Hello everyone, so welcome to class 26. So in this class we will be looking at certain standard I wrote here popular structures without really meaning that these mean crystal structures, because crystal structure has a particular connotation. There is a so a lattice plus basis, so that's the sort of crystal structure that has a particular connotation. But here by structure what I mean is structure derived out of some name of a mineral, and there are several such compounds which have a similar structure. For example, if I call something a perovskite structure, we looked at this, right. Something which has a chemical composition AbO3, where A is a cation, B is a cation, O is oxygen, or O can be any anion also, right. So this has a particular structure, right. So A atoms sit in the corners of a cube, or something that looks like a cube. It does not need to be a cube, there is a pseudo cubic unit itself, that is what we said. B atom sits in the body centered position and oxygens form an octahedron. Now this octahedron can be distorted, so the symmetry does not need to be cubic, right. So the crystal system does not need to be cubic, so it says nothing about that, but it is a group of materials or class of compounds that have the chemical composition AbO3 and that take this corner to corner octahedron connected structures as perovskite structures, right. So perovskite is the name of a mineral, right. Similarly we said something like so in the previous class we were looking at zinc blende structure. Okay, so before zinc blende we were actually looking at diamond cubic structures. Right. Now diamond cubic, silicon or germanium or diamond itself, right. So take the diamond cubic structure, and they have a space group of Fd3 bar m. We have looked at, visualized these structures, we have seen what is the point about which there is an inversion, there is a 3 bar there is a 4 bar 3m symmetry, and what is the point at which there is an inversion symmetry, right. So these two are not necessarily the same points, however and there is no one point about which there is the so an underlying symmetry of this, which is m3 bar m, right. So this is what we saw in the previous class, right. However, the entire structure together, the diamond glide, right, renders the underlying symmetry to be more than every single point in the crystal, right. So the underlying symmetry is m3 bar m. Right. So and the material property wise, the material behaves as if it has an m3 bar m symmetry. Okay. So that is what we looked at, and from diamond cubic we said, all right, so now instead of, so these are bunch of tetrahedra arranged in a certain very ordered fashion, and so the center of this tetrahedra, the tetrahedral central position is also occupied by the same atom as is occupied by the edges of the tetrahedron, right. So that is, and then all of them are sort of arranged in this very nice and nice manner where you do not lose the 4 bar axis of symmetry, and so on and so forth, right. So this is going to be an Fd3 bar m structure. However, I take the central atom of every tetrahedron and I am going to replace it not with silicon but with something else, right. So I am going to replace the central atom. The central atom of the tetrahedron is going to be different compared to the corners of the tetrahedron. Then we have arrived at what are called zinc blende structures, and ZnS itself, ZnS is zinc blende, it is a mineral, and ZnS itself has a zinc blende structure, and so the you lose out on the inversion symmetry, which is supposed to be this point here, right. So in silicon, this is the point of inversion symmetry, the 181818 points are points of inversion symmetry, but here you lose out on the inversion symmetry, and then you end up with, again, F centering is there, however now I have 4 bar 3m sort of a space group, right. So I don't so I don't anymore have the underlying symmetry to be m3 bar m, whereas the underlying symmetry is just 4 bar 3m, right. So that symmetry even exists in silicon, right. So there is the origin has a 4 bar 3m symmetry. Here also the origin has 4 bar 3m symmetry, but the entire crystal conspires to have nothing more than a 4 bar 3m symmetry. It has a 4 bar 3m symmetry only, okay. And 4 bar 3m does not have inversion symmetry, so zinc blende can be is in fact a piezoelectric material. Same with something like cubic zinc oxide, for example, that is also piezoelectric. Cubic boron nitride, for example, that also takes the zinc blende structure, and that's also so cubic zinc oxide, cubic boron nitride, right. So all these have similar structure as the zinc blende structure. So all these compounds put together, you call that it has a zinc blende structure. Okay. Now the analog of zinc blende, right, so are what are called Wurtzite structures. But these are not, so I am going to call it as hexagonal analog. Hexagonal, I mean not analog really, but to for lack of a better word, to loosely put it, hexagonal sister of the zinc blende structure, or not ZNS, but let me write it as zinc blende structure. Is what is called a Wurtzite structure. Now Wurtzite structures are very important. Now materials such as aluminum nitride, gallium nitride, right, then I have zinc oxide, the Wurtzite zinc oxide, right, so it is called hexagonal zinc oxide, right. So all these are good, all these crystallize in what are called Wurtzite structures. Now some of them, such as cadmium cadmium telluride, the image that I am going to show, right. So cadmium sulfide and all these things, they can take both. So these are what are called 4,6 compounds, right. So these are optically very active, right. So these are actually direct band gap materials which have good photoluminescence and so on and so forth. So they can take both the hexagonal Wurtzite like structure as well as zinc blende structure. So both of them, both the polymorphs exist, right. Just like boron nitride, for that matter, boron nitride can take the Wurtzite structure, but it also can exist in a cubic boron nitride structure. There is another HBN, which is a 2D material, right. So that we are not going to talk about right now. Okay. So all these things, so they all these compounds, they take what is called Wurtzite structure. Now let us take a look at so let us try to visualize this structure. Okay, so what I am showing on the screen here, this is a zinc blende structure, right. So if I see it along the A axis, it is nice, and all these tetrahedra are arranged in the form of, so if I just see a projection along the A axis, it looks like squares, right. Although you know that these are actually tetrahedra. The zinc atom, which is the gray atom, is surrounded by 4 along the tetrahedral corners I have the sulfur atoms that is surrounding the gray atom, right. So now if I visualize it along the let us say there is if I see it along the 1 1 1 axis, so I am going to change the orientation now, right. So in my visualization to be, the projection vector is going to be 1 1 1, and so I have to give a vector which is in plane, which is the upward vector, which is going to be 1 minus 1 0. If I apply that here, I see clearly that okay, so there should be a 3-fold axis of symmetry at least, right. So so if I rotate this entire structure by 120 degrees, so let me apply this again and then rotate this by 120. Well, this way nothing has changed, this way again I rotate, nothing has changed, right. So you can pay attention to the axis. I rotate it again, the axis have changed, but the crystal, so it does not seem like anything in the crystal has changed. So there is a 3-fold axis of symmetry, and in fact that passes through your origin. Okay, so about the 1 1 1 axis there is a 3-fold axis of symmetry, but since it is cubic, about the 1 1 1 bar also, right. So I can show you that very quickly. So I am going to visualize this along 1 1 1 bar. So if I look at the orientation, I am going to do the projection vector along 1 1 minus 1, and I am going to view the upward vector is going to be 1 0 1, that is going to be perpendicular to the projection vector. Again it is the same thing here also, I can rotate by, let us say, 120 degrees, 240 degrees, well, nothing is really changing, right. So at least in the center forget the corners, I'll have some edge effects there, but at the center nothing is really changing. So there is, so all the 111s are in fact threefold axis of symmetry. So you can see all the different symmetries that you have just by trying to understand the structure. I can play around, I can rotate, I can see how these atoms are arranged, etc., right. Now one particular way in which these atoms are arranged is something like this. Now what exactly am I showing you here? Let me properly do it with orienting it properly. So I am going to orient it along a projection vector which is going to be 1 1 0, and I am going to watch it, or 1 minus 1 0, and I am going to watch it about the upward vector 1 1 1 in a cube, right. So all these are equivalent directions, right. So 1 minus 1 0 1 1 0, right. So all these are equivalent directions, and if I apply this, I see now that so the tetrahedron, this is this particular unit, right. So this yellow atom here, right. So I don't know if you are able to see my cursor, but try to follow my cursor, right. So this yellow atom here, this yellow atom here, this yellow atom here, and there is one yellow atom behind that I am not able to see. So all these 4 yellow atoms form a tetrahedron. So I am watching the tetrahedron along a certain projection, and then the gray atom here is nothing but my zinc atom, right. But how am I seeing the tetrahedra in this projection? I am seeing that there is a zinc and sulfur, zinc and sulfur. There are these dumbbells of zinc and sulfur, right. So this is the 1 1 1 direction. The upward vector is the 1 1 1 direction, right. So I don't think I can write here, but the upward vector is 1 1 1 direction, which is the body diagonal of a cube, whereas I am seeing the crystal along the 1 1 bar 0 direction. Okay, so then I have these dumbbells of zinc and sulfur, and this is a manifestation of the tetrahedron, which are aligned parallel to each other. So they are all in the same orientation, right. So all these dumbbells are parallel to each other, and they follow the same orientation in the plane below, in the plane below, in the plane below, and so on and so forth. In all these planes I have dumbbells of this tetrahedron. Okay, and in fact you can see that if I call this a stacking, right. So this is going to be so if I draw this, so how is the dumbbell looking? Yeah, so I am going to draw a zinc, this one a zinc, this one a zinc, this one a zinc, this one a sulfur, right. And then so I am going to move this by 1/3 the lattice parameter, and I am again going to draw a zinc and sulfur, zinc and sulfur, zinc and sulfur, zinc and sulfur, and then so the third layer is going to translate by 2/3, and then I am again going to draw a zinc and sulfur, zinc and sulfur, zinc and sulfur, and the fourth layer, right, so of this dumbbell is going to shift by one complete okay, so maybe I have to draw it more carefully. So this is going to be zinc and sulfur, zinc and sulfur, zinc and sulfur, right. And then the fourth layer is going to exactly come below the first layer. So there is going to be zinc and sulfur. Okay, so it didn't come out very well, but yeah. So if this is going to be an A stacking, this is going to be a B stacking, this is going to be a C stacking, then A, B, C repeats, right. So this will be again A stacking, B, C, and so on and so forth, right. So that's how the cubic structures look like. So there is going to be an ABC, ABC, ABC sort of stacking. This is just like in metals, right. So I'll also show you the example of metals, FCC metals, which also have a similar sort of stacking, right. So this is also a face centered structure, which is a zinc blende structure. Okay. So but remember the orientation, that all these dumbbells are oriented in the same direction. Okay. So now I am going to go to a Wurtzite structure. Now what is a Wurtzite structure? If I look at the space group, so from now on so if I look at a new structure, I am going to ask the question, what is the space group, what is the underlying symmetry, and if underlying symmetry so what are the polyhedral units that are in this, right. So here also I have tetrahedral units, right. So for example I can clearly see that so these are all tetrahedra. So there is this is aluminum nitride. So, aluminum is at the center of the tetrahedron and it is surrounded by 4 nitrogens, right. So, okay, so this is also a tetrahedra of aluminum AlN4 units which are connected with respect to each other. Okay, so that's from a polyhedral perspective, that's the structure. However, if I look at the structure of this, right, so edit data, I go to the unit cell, it turns out that this is a hexagonal structure, it is not a zinc blende structure, it is a hexagonal structure, right. So, I have one 6-fold axis of symmetry, in fact, I have a 6-3 axis of symmetry. If I see, you know, and what does this 6-3 mean? This 6-3 means that, you know, so if I actually look at it, so because of the 6-3 symmetry, so this is the analog. So, I am just, you know, if I look at the tetrahedra, I am just connecting them in slightly different fashion, right. So, compared to what the cubic structure is, right. So, for example, all the tetrahedra here are in the same orientation, whereas in the next layer, I am going to flip the tetrahedra by 180 degrees and then, you know, so connect them together, right. So, and in the next layer, I am again going to flip the tetrahedra back. And then connect them together, right. So, this flipping the tetrahedra by 180 degrees, right, this can be, you know, gotten by an operation of 6-3, right. So, I have a 6-fold axis of symmetry, but you know, so I rotate the tetrahedra by, you know, 30 degrees, or, you know, so 30 degrees will be similar to 180 degrees in when I translate by half a unit cell, right. So, this is going to be the unit cell C is here, you can see my you can look at my arrow here, right. So, I have the unit cell is plotted here in the dark rectangle, right. So, half of the unit cell, right. So, that is the 6-3 symmetry. At half of the unit cell I need to have a screw axis, right. So, my dumbbell which is here now rotates, right, and then comes out of the plane, but that is 180 degrees of the rotation. Okay. So, every second plane is rotated by 180 degrees, that is the meaning of a 6-3 symmetry with respect to the first plane. So, every second tetrahedron, every tetrahedron which is on the top of each other is rotated by 180 degrees, right, whereas this does not happen in zinc blende. In zinc blende all tetrahedra are stacked on the top of each other, they are in the same orientation, right. Now, as a result, if you see the tetrahedral if you see the Wurtzite structure, right, that's the basic difference between a zinc blende and a Wurtzite, right. Now, it turns out that many materials can either crystallize in Wurtzite or zinc blende, they are energetically sort of equivalent, like I was telling you cadmium telluride, right. Energetically the zinc blende and the Wurtzite structure are sort of close to each other, that, you know, if I am growing cadmium telluride I can get both the structures, right. Now, if I get both the structures and I want to actually resolve these structures by looking at it in a transmission electron microscope, right. So, if both of them are equally stable, right, so then when I am growing cadmium telluride both of them will form, right. Now, the question is which one forms, or do both of them form, right. So, and then how do I resolve it, right. So, that is the question. We will do transmission I will show you some transmission electron microscope image to actually identify this. But here you can actually see that, you know, so there is nitrogen aluminum, right, but the next dumbbell, so if I am just looking at it in this orientation, right, I am not going to see the bonds, okay. So, I am just going to see the dumbbells, right. So, I am going to see one plane of dumbbells which are all in the same orientation, nitrogen aluminum, nitrogen aluminum, nitrogen aluminum, and so on and so forth. But in the next plane, right, so if I go above the along the C axis, right, which is equivalent to the 1 1 1 direction in a cube, right. So, the body diagonal in a cube becomes the C axis in the hexagon, right. So, that is the 1-to-1 correspondence. But along the C axis, right, the next dumbbell should actually, you know, change it's going, if this is zig, this is zag, right. So, I have to see the zigzag sort of an arrangement along the C axis, right. So, if I see this sort of a structure, I am going to call it Wurtzite, right. Now, let us actually check this out, right. So, I was showing you this is the image of cadmium telluride, right, which was grown nanowires of cadmium telluride, which was grown using a process called vapor liquid solid process, but that does not matter, vapor liquid solid process. But the exact details of the process are not very important here. You can see that cadmium, so let us again I failed to check which one is the heavier atom, but let us just assume for the sake of argument that cadmium is slightly heavier than tellurium. I think there is an atomic difference, number difference of about 2, right. So, you do not see much of a contrast difference, but let us say this is cadmium, this is tellurium, this is cadmium, this is tellurium, this is cadmium, this is tellurium, right. So, here I see a zinc blend sort of an arrangement, right. So, all in along all these layers, right. So, this is my C axis, okay. So, along all these layers the cadmium and tellurium, right. So, all these dumbbells are aligned sort of in ABC sort of stacking, right. So, this is a zinc blend like structure, right. But immediately, right. So, very coherently and immediately it changes to, you know, so a stacking where along the C axis I have a dumbbell which is let us say this is cadmium, this is tellurium. So, this is again cadmium, right, but this is tellurium. But again here again this is cadmium, this is tellurium, right. So, this is cadmium, tellurium, cadmium, tellurium. So, now and then again this is cadmium, tellurium, right. So, the dumbbells have changed their orientations, now it becomes a zig zag zig sort of thing, right. So, in this part of this is a 3 layer domain, right. So, if I am actually looking at this becomes a zig zag sort of, you know, arrangement about the C axis. So, you see, so the tetragons the tetrahedra, right. So, here are in the same orientation about the C axis, that gives it a zinc blende structure, but here they are, you know, sort of rotated with respect to each other along the C axis, okay. That gives a zinc blende structure, sorry, that gives a Wurtzite structure. Both Wurtzite and the you know the zinc blend, both of them are energetically equivalent, I mean, so almost equivalent in this case, right. So, so as a result you have both the phases forming, and both these phases are forming within, you know, so if I look at, there are hardly 1 2 3 4 5 6 6 layers of zinc blend, and you know, so 1 2 3 4 5 layers of Wurtzite, right. So, hardly, or 6 layers of Wurtzite, right. They are sort of periodically forming, right. So, Wurtzite zinc blende, Wurtzite zinc blende, Wurtzite zinc blende, and so on and so forth, right. So, typically materials tend to do this, right. So, and they are very coherent with respect to each other, right. So, both structures can exist, similar lattice parameter, they can coherently grow on the top of each other, right. So, this is zinc blende structure, this is Wurtzite structure, but there is nothing to say that, you know, so I have any dangling bonds at the surface or whatever, right. So, they are nicely sitting on the top of each other, right. So, both of them coexist, both of them are, you know, they are it has 2 different structures coexisting beautifully in one material, right. So, if I have similar stability of 2 different materials of 2 different phases in a material, and they both can be coherent just like zinc blende and Wurtzite, the only difference between zinc blende and Wurtzite is how you rotate the tetrahedra, right. So, in zinc blende you do not, in Wurtzite every alternate layer you are rotating the tetrahedra by 180 degrees, but that is okay, right. So, both of them are similar in energy, it is very small energy penalty that I have to spend by going from zinc blende to Wurtzite. So, both of them will form, right. So, there is no particular selection that the material will do, okay. So, this is an example of zinc blende and Wurtzite structure. Excuse me, today I am coughing a bit, so I apologize for that in advance. Okay, so now what are the other features I can see? I can look at you know, what are the Wyckoff positions, I can actually look at the structural parameters. Where is aluminum? Where is nitrogen? Right. So, if I go back to edit data, and then I look at the structure parameters. In fact, you see that all the aluminums are sitting at 0.36, 0.33, 0.66 and 0 along the z axis, but you know so along the x axis it is 1/3, right. So you know, so in our hexagonal unit cell we are placing aluminum at 1/3, 2/3 and then 0, whereas the nitrogen is not being placed at 0.3, 1/3, 2/3 and 1/3, right. So that would be centering of nitrogen. However, the nitrogen is slightly, you know, off centered. So, it is off centered from this you know if I consider this aluminum tetrahedron, the nitrogen is a bit off centered, right. So, nitrogen is moving a bit along the C axis. As a result, you know, so there is the nitrogen, I mean we can calculate the polarization that is developing. This also will have a spontaneous polarization because nitrogen is not exactly sitting at the center of this tetrahedron. Nitrogen is moved slightly towards one part of the aluminum and not the other part of the aluminum, right. So, we can actually estimate what is the polarization of aluminum nitride. I will give that as an assignment problem that you should be able to do. It turns out that the spontaneous polarization, if this is the plane of nitrogen, right. So, the spontaneous polarization will always point to the plane of the nitrogen, right. So, in these structures, right. So, given this sort of an arrangement of aluminum and nitrogen, the spontaneous polarization will always point to the plane of the nitrogen, okay. And this has some significant spontaneous polarization. In fact, the big deal about aluminum nitride is a very good piezoelectric material. It has a space group of P63MC, which means the underlying point group is 6 mm and 6 mm is a polar group, right. Since it is polar, it also has, I mean I should not be saying that, it also has a spontaneous polarization, which I am not going to give you the value because I will ask you to calculate in an assignment. Just by looking at the structure of nitrogen, so just like we calculated it for barium titanate, we should be able to look at the structure and then see how much nitrogen is displaced from the center of the tetrahedron and calculate the spontaneous polarization, right. And the spontaneous polarization points towards nitrogen planes, right. So, if I am growing, let us say I am doing a process what is called an MOCVD process, right. So, this is metal organic chemical vapor deposition. I am not going to go into details of what this process is, but this is how I grow. This is one of the standard ways by which I grow thin films of aluminum nitride. I am going to grow what are called thin and single crystalline films. In fact, in IISc I offer another course which is about the growth of these such sort of epitaxial films, what is the science that goes behind this, right. So, that is not part of this course, but let us assume that there is a technique called MOCVD with which you can grow layer by layer, right. So, I can grow aluminum followed by nitrogen, followed by aluminum, followed by nitrogen and so on and so forth, aluminum, nitrogen and so on, okay. Now, I have to end it somewhere, right. So, if I end it at nitrogen, right. So, this is what is called an N polar structure, right, and the spontaneous polarization is assumed. I mean I will ask you to, I will make you do the calculation in an assignment. So you will calculate that the spontaneous polarization always follows the nitrogen plane. So, it is going, so the charges end there, right. So, I will always have a positive charge which is accumulating at the nitrogen plane, right. Whereas, if I grow in such a way and then I will start growing some other material here, right. So, if there is aluminum nitride, I will start growing some gallium nitride or something like that, right. So, I will grow something else, but the spontaneous polarization of aluminum nitride sort of ends with the nitrogen plane, okay. But if I grow it in such a way that let me again draw it in green. So, this is now if I grow it in such a way that I end with aluminum, not nitrogen, right. So, this is nitrogen, but again there is some gallium or something here, nitrogen and so on. So, this is a different material, whereas this is nitrogen, this is aluminum, this is nitrogen, this is aluminum, this is nitrogen, this is aluminum, this is nitrogen, this is aluminum. So, if it is aluminum polar, right, sorry. If it is aluminum polar, then the spontaneous polarization of this will be facing down, right. So, facing towards always a nitrogen plane, okay. So, if my material starts with a nitrogen plane, spontaneous polarization is pointing down. If my material ends with a nitrogen plane, that means it started with an aluminum plane, right. So, just to maintain this continuity in the growth. So that means that the spontaneous polarization is pointing up. So when you hear things like N polar, aluminum polar, you will actually calculate in your in your assignment what is the direction of spontaneous polarization. Okay. So N polar, I mean you can always take it as at the tip of your finger that polarization is always pointing towards my nitrogen plane. Okay. Okay, fine. So that's those are the little details about Wurtzite structure. The other Wurtzite, important Wurtzite structure is what is called gallium nitride, right? Now what people do is actually they grow structures such as this, right? So here you have, this is gallium nitride, right? So this is a very epitaxial sample of gallium nitride, just like what I said right now, right? So in gallium nitride, so this is let's say and this is what is called aluminum gallium nitride, right? Now depending on the polarization, right? So aluminum gallium nitride, right? So this is going to be ending with nitrogen plane, right? So I have positive charges, so the polarization is pointing this way in aluminum gallium nitride. And in gallium nitride, gallium nitride starts with a gallium atomic plane and ends with a nitrogen atomic plane. So the polarization of gallium nitride is also like this, right? So this is polarization of aluminum gallium nitride, and this is the polarization of gallium nitride. Okay. Now I have an interface, right? So here I have aluminum gallium nitride and here I have gallium nitride. So which means I have an interface between aluminum gallium nitride and gallium nitride. Both of them have different polarizations. So I have a polarization of aluminum gallium nitride, which is as much, right? And then I have a polarization of gallium nitride, which is ideally a bit different, right? Now this is your problem of electrostatics, right? Ideally, so if I have a polarization, so one of your Maxwell's equations would say that polarization dot n, right? So that is polarization in the direction perpendicular to the surface, okay, should be equal to 0 if there are no free charges. Okay. So that actually comes to that actually gives you a constraint that if I look at polarization component which is perpendicular or along the let's call this direction as direction 3, right? So P3 in material 1, okay, minus P3 in material 2, okay, ideally this should give me some sort of so the only way these two can be different is if there is some sort of charge accumulation here. Only way, this is just simple electrostatics. You can go back and look at your Griffith's book on electrostatics about the boundary conditions for Maxwell's equations, right? Griffith's for electrostatics. You will see that the only way the polarization of aluminum gallium nitride is not equal to the polarization of gallium nitride is if the interface has some extra charges. Okay. And it turns out, so the polarization, so the number of, let's say I am collecting positive charges because of the polarization of this is AlGaN polarization, but because of GaN polarization I have it starts with less number of negative charges. GaN has lesser polarization, right? So to compensate for these extra charges, there are 5, I mean, so the way I drew it, right? there are on the algan side, right. So, this is the GAN side. At the interface, on the algan side, right, how many charges do I have? I have 1, 2, 3, 4, 5, 6 positive charges. This is just some schematic explanation, right. So, there are 6 positive charges. That is because polarization of algan is greater than polarization of GAN, which means the number of charges that it places on the plates, right. So, that is polarization, right. So, the number of charges, that positive charges it places on this plate, bound charges, is larger than the number of positive charges than the number of negative charges that GAN will place on the negative, on the other side of the plate, right. Whereas, there are 4 negative charges given by GAN, right. So, now interface hence cannot be charge neutral until I create 2 more charges, 2 more negative charges. Okay. And it turns out that these negative charges are free electrons, because it is not necessary that charge should always be bound, right. So, in this case the bands bend in certain way, right. So, let us not go into the details of it, that here at the interface what comes up are actually I need more negative charges at the interface, otherwise this polarization continuity is not going to be maintained. The only way polarization continuity is going to be maintained is if I have more charges at the interface, right. And more charges can be created by bands bending in a certain way. Here the conduction band comes below the Fermi level, creating some sort of free electrons there, right. So, free electrons are created. Just because I have a this is called polarization discontinuity, right. So, let me go back. So, what I have in case of GAN algan heterostructures, these are called aluminum gallium nitride, both of them are Wurtzites, right. Both of them are Wurtzites, but both of them have different spontaneous polarizations. So, then I am going to create what is called a polarization discontinuity, which given the band structure of algan GAN, that is compensated by by free electrons. Okay. So, what do I have here? I have an aluminum gallium nitride, which is a very nice insulator, right. This can conduct only at, let us say, only at the core of sun. Okay. Then I have gallium nitride, which is known to be a wide band gap semiconductor. This is what is called a wide band gap semiconductor. This also conducts at the this is at the surface of sun, this is at the core of sun, or the other way around. I do not remember the band gaps of I think aluminum gallium nitride is a bit lower than gallium nitride, but so the band gaps are so huge, right, that they do not conduct ordinarily, right. So, you have to heat it to such a high extent that is only when they will start conducting. So, this is a sort of an exaggeration, this is less science and more sort of driving home the point, right. So, core of sun does not mean I am literally taking it to the core of sun temperatures, it means that I really need super high temperatures for it to conduct. At room temperatures it is a perfectly nice insulator, right. Same thing with aluminum gallium nitride. Aluminum gallium nitride, if I am not doping it at room temperature, it is a perfectly very capable insulator by itself, right. So, now I put two insulators together on the top of each other. Okay, so I have to create a new page. I put these two insulators on the top of each other. Magically, right, I am creating some free electrons here. Right. I put two slices of bread and magically the sandwich is created, right. So, this is bread 1, which is gallium nitride, this is bread slice 2, this is aluminum gallium nitride. I just put them together, I make a very nice interface. If I make a very nice interface, the only way this interface can stabilize is if I create the sandwich, right. The sandwich, the jam or the cheese comes by itself, right. So, this is automatically created. And what is this sandwich? The sandwich is so it's a set of free electrons, or it is a gas of free electrons. Okay. So, if I actually measure the conductivity, this is going to conduct. I have two insulators which I put together, I make a sandwich, and this magically starts to conduct. It conducts like a metal. Okay. So, so this is what is called the 2D, I mean, and it's just 2 dimensional, right, it is just at the interface. Actually, this is real 2D, right. So, it exists atomic layer thick, and it is only at the interface, right, only at the interface between aluminum gallium nitride and gallium nitride, right. So, this is what is called 2D electron gas, 2D electron gas. How did we generate this? We generated this by just combining two materials with different polarizations, that is it, two Wurtzite materials with different polarizations. Okay. Okay, so fine, okay, so there is some magic of material science has happened, and then I have magically created this 2D electron gas. What is the use of it, right? So, now this 2D electron gas, right, so for people who are interested in devices, is a ready made electron channel for you, right. So, if you are thinking about transistors, in MOSFETs, you have to create a channel by applying some gate voltage, right. So, here you already have a ready made electron channel, now you have to switch it off and switch it on. So, you can use it as a transistor. And it turns out that this is created because of differences in polarization, right, and this is a very high mobility gas, which means that the resistance for flow of these free electrons is very small, right. So, this is a high mobility electron gas. So, as a result, what you make out of these, the transistors that you make out of these structures are what are called HEMTs, or high electron mobility transistors. Okay. This is the theory, okay. But I want you to actually go back and then so this is a take home or as I would say in my classes, right. So, there is no way of checking this in an NPTEL course, but let me give you an impromptu reading assignment. If you do not know what mobility is, now is a good time to understand understand what mobility is. Of any carrier, essentially mobility is and then number 2, try to get in, so try to familiarize with yourself with the values of mobility. What are the typical values in let us say a p-type silicon? Let us say in MOSFETs, right. So, what are the maximum mobilities you can get, maximum electron mobility? These are various questions, right. So, in a MOSFET, if I have what is called a PFET, sorry, PMOS, right. So, what is the maximum hole mobility that one can get in MOSFETs, right. So, metal oxide semiconductor field effect transistor, and then compare it with mobility values obtained in HEMTs, right. So, these electrons are much faster. As a result, you can use, since the electrons actually travel much faster, you can use these HEMTs for what is called gigahertz electronics, which means that the mobility of electrons should at least, so if I have gigahertz pulses, right. So, the electrons should actually respond to these gigahertz pulses, right. So, they cannot move slower than gigahertz, right. Whereas in normal transistors that may not be the case, that is not the case indeed in silicon transistors, right. So, if you want for gigahertz electronics, you may want to use HEMTs, right. So, that is the, it is a basic idea of what HEMTs is, and this is not a transistor course, so I am not going to details of this. These are the keywords that you can actually search and then find out for yourself, and then the key point here being fundamentally what I am doing is I am creating a polarization discontinuity in couple of Wurtzite structures, and by creating this polarization discontinuity, what I am doing is I am bending bands in such a way that the only way this polarization discontinuity can be compensated, charge compensated, is by adding some extra electrons. And these are free electrons. Since they are free electrons, they can move around, right. I can apply voltage and then move them around, and then these electrons, so they are hugely mobile. There are not many defects, right. So, on these very nice structures that I have created, so they are very highly mobile, and since they are very highly mobile, they are very fast. I can use these sort of transistors with the so called HEMTs in gigahertz electronics, right. So, to do electronics in gigahertz, which is 10 power 9 hertz, right. So, typically if I do any sort of capacitance measurements, etc., that will be in megahertz, right. So, with normal probes or even sub megahertz, but this is to do measurements in gigahertz, right. So, or not measurements, not just measurements, but applications in gigahertz, you may want to use these sort of transistors, which are high electron mobility transistors. Okay. So, the fundamental underlying material science aspect here is I combine two materials with same structure, Wurtzite structure, same symmetry, but different spontaneous polarization. That is it. Okay. And rest is the beauty of physics and spontaneous polarization, discontinuity. Okay. So, with that, let me end here this lecture, and I will see you again in the next class.